On this problem, we're going to roll a red die and a blue die, and we want to find the chance that at least one is a 6. Now, forgive me for a minute, I'm going to pretend like I have forgotten the complement rule to make a point to show you why we need the complement rule. So if I was going to roll these two dice, and I want to find the chance of at least 1 6, when we do probability, the biggest thing that we need to remember is list out what are all the possible outcomes that will give you what you want. So if you want at least 1 6, we could do like the red is a 6, and the blue is a not 6. That would be one outcome. We could do, let's see, red as a not 6, and we could have the blue is a 6, because either of those would have 1 6. We could also do a red is 6 and blue is 6. Now, on these, when I say like red is not 6, that means it could be a 1 through 5. I really don't care what it is, just as long as it is not a 6. So here are 3 different possibilities to give me what I want. And if I want to find the probability of at least 1 6, I'm going to need to find the probability of each of these and then add them up. So like the probability of red 6 and blue is not 6. Well, the red 6, there's a 1 in 6 chance to get a 6. And for blue to not be a 6, there would be 5 numbers that are not a 6. That's using the complement rule just in a little step right there. Okay, so if 1 is a 6, that means there's 5 numbers that are not a 6. We're going to multiply because it's an and. Okay, the 2 dice should be independent. They shouldn't be affecting each other, so I don't have to worry about that second probability of changing it somehow. Okay, the probability of the next one for red is not 6 and blue is 6. Well, let's see, we want red to not be 6, so that would be 5 6. Times blue is 6, that would be 1 6. Now for the last one, if I want red to be 6 and blue to be 6, well, we have a 1 6 chance of getting red as a 6, and for the blue to be 6 would also be 1 6. So we would have to find each of those and add them up. So now my final probability I want to get of at least 1 6, well, that's going to be this 1 6 times 5 6 plus 5 6 times 1 6 plus 1 6 times 1 6. And if I put that in my calculator, I should get something like 11 out of 36. Or if you want to change that into a decimal, because I think decimals are easier to work with, 0.3055. So that's how you can do the probability of at least one the long way. Now this wasn't too long. I only had to find 3 different probabilities. It's really not that hard. But if I rolled even 3 dice, there's a lot more probabilities that I have to find. And if I wanted to roll 6 or 10 dice, you're never going to finish this problem if you're trying to do it the long way. So that's why we invented the complement rule. The complement rule is useful for things like to say if you have a 1 6 chance of rolling a 6, then that means you have a 5 6 chance of rolling a not 6. So it's useful for knots, but it's also very useful anytime you want to find the probability of at least 1. We're always going to use this trick for at least 1 because it saves us so much time for bigger problems. Because the probability of at least 1 6 is always going to be equal to 1 minus the probability of no 6s. Okay. The reason why is when we looked up these outcomes, those were the outcomes that gave us what we wanted. The only other option left is no 6s, or the complement of at least 1 6 is no 6s. So the probability of no 6s, the only way you're going to get that is if you have red not 6 and blue not 6. So notice, even on this stuff, when I use the complement rule, I'm still thinking of like what outcome gives me what I want, or in this case with the complement rule, what I kind of didn't want. So the only way to not get at least 1 is red is not 6 and blue is not 6. Okay, the probability for that, red to not be 6 would be 5 out of 6 times, and blue not 6 would also be 5 out of 6. And this also gives me 11 out of 36 is my final answer. So notice the complement rule just says, oh wait, I remember anytime I want to find the probability of at least 1, that's always going to be equal to 1 minus the probability of none. So then we only have to find this one probability, which especially on bigger problems saves me so much time.